Every physicist agrees on one thing. Nothing can travel faster than light. Not a ship, not information, not even hope. If you cross that line, you break the universe itself. So why did a real physicist publish a paper showing how to do it? In 1994, buried inside Einstein's equations, Miguel Alcubierre found something disturbing. Not an error, not fantasy. A mathematical path around light speed. He wasn't trying to cheat physics. He was following it, line by line. And the deeper he went, the more it looked like the universe had left a door unlocked. Here's the terrifying part. He didn't try to make a ship move faster. He asked a different question. What if the ship never moves at all? That sounds impossible. Until you remember something strange. The universe itself is expanding. Galaxies are separating faster than light, and physics allows it. So the speed limit isn't about moving through space. It's about how space behaves, and space doesn't follow the same rules. Alcubierre proposed compressing space in front of a ship, stretching space behind it, a ripple, a distortion, a bubble. Inside that bubble, the ship would sit completely still. No engines blazing, no breaking light speed. Space itself would carry it. On paper, the math worked. The equations from Einstein didn't reject it. They allowed it. That's when this stopped being science fiction. Because if the math is valid, then faster than light travel isn't forbidden. It's just hidden, but every door has a lock. And this one demanded a price so extreme it almost killed the idea instantly. The energy requirement wasn't just massive. It wasn't just astronomical. It was unthinkable. Early estimates suggested you'd need more energy than exists in the entire observable universe, not to travel fast, just to start. Not a power plant, not a star, not a galaxy. Every photon, every atom, every joule of energy that exists, all of it. And it still might not be enough. But energy alone wouldn't save you. The equations demanded something stranger, something we've never created, never touched, never held. Negative energy. And no, that's not what you think it means. Not low energy, not zero energy. Energy that drops below zero, as if the universe could go into debt, as if nothing could somehow owe you something. Physics does predict tiny slivers of negative energy. Quantum effects like the Casimir phenomenon can produce them, but only in microscopic flickers, vanishingly small. You couldn't power a light bulb, let alone a starship. So the warp drive was shelved, declared impossible, a beautiful, seductive equation with nowhere to go. The kind of idea that makes physicists sad, or so it seemed, because years later, a researcher at NASA quietly closed his office door and started running the numbers again. His name was Harold White, and he didn't think Alcubierre was wrong about the concept. He thought he was wrong about the math, specifically the scale. What if the energy requirement wasn't the size of the universe? What if it was the size of a planet? Still laughably impossible, but for the first time, not infinitely impossible. That distinction matters more than it sounds. White changed one thing: the shape. Instead of a sphere, he proposed a ring, a torus-shaped warp bubble, a subtle geometric tweak, and it quietly broke the math wide open. The energy requirements collapsed, from universe-sized to something closer to the mass of Jupiter, still outrageous, still far beyond us. But for the first time, physics didn't laugh. It leaned in. And that shift unlocked a darker, stranger question. If space can be bent by a machine, could it already have been bent by something else? Some physicists began asking whether advanced civilizations would even bother with rockets. Why push through space when you could fold it? Why travel the ocean when you could move the shore? But warp drives carry a warning label that most people miss. They don't just bend space. Under the right conditions, they begin to bend time. Certain warp configurations could produce closed time-like curves, a loop in spacetime, a road that bends back on itself. In plain language, a path into the past. And that's where physicists go quiet, because the moment time travel enters the equation, cause and effect stop being reliable. The universe stops making sense. Some researchers believe reality has a defense mechanism, that quantum effects would tear a warp bubble apart before it ever fully formed, before any paradox could take hold, almost like the universe has rules and enforces them. So the question remains open. Is the warp drive a glimpse of what physics will one day allow, or a beautiful trap? An equation that teases forever and delivers nothing? Right now we have none of what it requires. Not the energy, not the materials, not even a theory for how to generate stable negative energy at scale. We're not close. We're not even pointed in the right direction. But we've been here before. Heavier than air flight was declared a fantasy. Splitting the atom was considered the stuff of madness. The history of physics is a graveyard of things that were impossible, right up until they weren't. The warp drive isn't an engineering problem, not yet. It's something stranger, a question buried inside Einstein's own equations, a question he may not have realized he was asking. And if the equations allow it, even quietly, even theoretically, then the universe is less of a prison than we thought. The speed of light may not be a wall. It may just be a door we haven't learned to open. But let's take a few minutes to take a deeper look. Here's what most people get wrong about warp drives. They think the ship moves. It doesn't. The ship sits perfectly still. Instead, space itself moves around it. The fabric of the universe contracts in front and expands behind. Like a wave, the ship rides without ever technically breaking the speed of light. Einstein's rules stay intact. The ship just found a loophole. Think of it like a moving walkway at an airport. You're standing still, but the ground beneath you is moving. Now imagine that walkway moving at 1,000,000 miles per second. That's the idea. You're not traveling through space. Space is traveling for you. But to create that wave, you need to physically bend space-time. And space-time doesn't bend easily. It's not fabric in any soft sense. It's the rigid structure of reality itself. To curve it the way a warp drive requires, you need something with almost unimaginable gravitational influence. That's where normal physics hits a wall. Gravity bends space. Mass creates gravity. So to bend space enough to move a ship, you'd need mass, or energy, on a scale that makes stars look small. Unless you use the other kind of energy, the kind that shouldn't exist. Negative energy. The term sounds like science fiction, but it appears in real physics equations, not as an error, not as a placeholder, as a legitimate solution, something the universe seems to quietly permit, in specific, strange, almost reluctant circumstances. To understand negative energy, you first have to understand something about empty space, because empty space isn't actually empty. At the quantum level, it seethes. Particles flicker in and out of existence constantly, appearing from nothing, annihilating each other, vanishing again. The vacuum is alive with activity we can't see. This isn't philosophy, it's measurable. In the 1940s, a Dutch physicist named Hendrik Casimir predicted that if you placed two uncharged metal plates close enough together in a vacuum, the quantum activity between them would be suppressed. Less energy between the plates than outside them, a region of space with less than nothing. And when scientists tested it, they found exactly that. The plates were pushed together by what should have been empty space. The Casimir effect was real. Negative energy wasn't just theoretical anymore. It was sitting in a lab, small, fragile, almost impossibly tiny, but real. The problem is scale. The Casimir effect produces negative energy in amounts so small they make a single atom look enormous by comparison. To power a warp bubble, you'd need to amplify that effect by a factor that doesn't have a name. We don't just lack the technology, we lack the concepts. But here's the thing about physics. It doesn't care about our engineering limitations. If the equations say something is possible, even if it's absurdly, laughably beyond us right now, that possibility doesn't disappear. It waits. Sometimes for decades. Sometimes for centuries. By the early 2000s, the warp drive was a punchline, a thought experiment that serious physicists mentioned only to dismiss. It lived in science fiction, in convention panels, in late-night conversations between grad students, not in funded laboratories, not in NASA hallways, until it did. Deep inside Johnson Space Center in Houston, there was a small lab, underfunded, easy to overlook. It went by the name EagleWorks, and its mandate, quietly approved by NASA, was to explore the physics of propulsion that had no business being explored, the impossible, the fringe, the things you weren't supposed to take seriously. Leading it was Harold White, an aerospace engineer and physicist who had spent years working on conventional propulsion, He wasn't a dreamer chasing fantasy. He was methodical, precise, the kind of researcher who doesn't make claims without data, which is what made what he did next so striking. White went back to Alcubierre's original 1994 paper, not to celebrate it, to interrogate it. He ran the calculations again from scratch, and he found something, a geometric assumption buried in the math, one that, if changed, cascaded through the entire equation and transformed the result. The original warp bubble was modeled as a sphere. White asked a simple question. What if it wasn't? What if the bubble was shaped more like a ring, a torus? The physics didn't forbid it. And when he ran the numbers with that adjustment, the energy requirement didn't just drop. It collapsed. Universe-sized energy requirements shrank towards something merely planetary, still impossible by any current standard. But the difference between requires all energy in existence and requires the mass energy of Jupiter is not trivial. One is a closed door. The other is a door that's locked, but has a keyhole. White published his findings, and then he did something almost no mainstream physicist would dare. He proposed an experiment, not a thought experiment, a real one, in a real lab, using real equipment. He wanted to try to generate a microscopic warp field, smaller than an atom, and detect it. The device was called the White-Jude Warp Field Interferometer. It used a precisely tuned laser split into two beams, one passing through a region where a tiny warp effect might exist, one passing through normal space. If the beams came back out of sync, even by a fraction of a wavelength, it would suggest space had been bent. Let that settle for a moment. There was a NASA lab, with a NASA physicist using NASA equipment, actively trying to bend space-time, not in a movie, in Houston, in a building with a badge reader and a parking lot and a coffee machine down the hall. In 2013, White's team released something that briefly stopped the internet. Visualizations from their computer modeling, showing what the optimized warp bubble geometry looked like. And to many eyes, it looked less like a diagram. It looked like a ship, structured, almost deliberate. The resemblance was eerie. The physics community did not celebrate. Skeptics pointed out that the visualizations were modeling outputs, not experimental results. That seeing a shape in a simulation proves nothing. That extraordinary claims require extraordinary evidence, and White had not yet produced that evidence. They weren't wrong. But White wasn't claiming success. He was claiming possibility. There's a difference between saying, we built a warp drive, and saying, the math doesn't forbid this, and here's an experiment designed to find out. Science is supposed to do the second thing. That's the entire point of science. Eagleworks continued quietly. Results were incremental, frustratingly inconclusive, the kind of data that doesn't make headlines. Small anomalies, measurement noise, results that might mean something or might mean nothing. The work that happens before breakthroughs that nobody films. Then, in 2021, something shifted. A separate team of physicists, working independently from White, published a paper claiming they had identified a theoretical workaround for the negative energy problem. A new class of warp solution that might not require negative energy at all. The paper came from Eric Lentz at the University of Göttingen. His proposed solution used a different geometric structure. Solitons, self-reinforcing wave packets in space-time. The math was dense. The peer review was intense. But it wasn't rejected. It was published, and it quietly rewrote the conversation. Suddenly, the warp drive wasn't just Harold White's project anymore. It wasn't just Eagleworks. Multiple independent research groups were publishing. The Fringe was becoming a field, slowly, carefully, with the particular caution of people who know they're being watched for mistakes. We still don't have a warp drive. We still can't generate the energy. We still haven't confirmed negative energy at any useful scale. We are extraordinarily far from building anything. But the question has changed. It used to be, is this possible? Now it's, under what conditions? That is not a small shift. Because that's how every impossible thing begins. Not with a machine, with a question that refuses to go away, with a number that keeps coming out wrong in interesting ways, with a small lab, a skeptical institution, and one researcher who couldn't stop running the numbers. Thanks for watching. It means a lot. If you want to see more videos like this, subscribe and leave a like. And if someone in your life would enjoy this, send it their way.